Hey guys, I'm John and welcome to Respect Your Intellect. Quantum tunneling is one of the most important phenomena of quantum mechanics because it plays an important role in nature as well as in our technology. So in this video, we'll cover everything that's important to know about quantum tunneling. Don't forget to hit the like and subscribe buttons, and let's get started. Let's start by talking about what quantum tunneling is. Remember in our introduction video to this series, we talked about an example of throwing a ball against a wall. While in classical mechanics, and depending on the ball, it could either bounce back to you, which is known as reflection, penetrate the wall and stop, which is known as absorption, or go through the wall if it contains enough potential energy to overcome the barrier. In quantum mechanics, though, this isn't necessarily the case. There's a phenomenon that allows particles to sometimes go through a barrier. The same example can be given with a ball and a hill. In classical physics, the ball would require enough potential energy to roll over the hill and get to the other side, or it would otherwise simply start rolling back down. In quantum physics, particles are sometimes able to simply go through the hill in the same way as the previous example. Quantum tunneling was discovered from the study of radioactivity in the early 20th century and became widely accepted about mid-century as a general and widely applicable phenomenon of quantum mechanics. The way that quantum tunneling works is again due to the wave-particle duality of particles in the quantum world. One interpretation of this duality involves the Heisenberg Uncertainty Principle that defines a limit on how precisely the position and momentum of a particle can be known at the same time. To put this in more simple terms, you can't know the position or momentum with absolute certainty because it would force the other to infinity. Because of this, you can't definitely prevent a particle's wave function from appearing on the other side of a barrier. All you can do is decrease the probability of tunneling to the other side by making the barriers taller, wider, or thicker to the point that tunneling simply doesn't happen anymore. This is precisely the reason why we can't continue to make transistors smaller in our computers, because electrons would start tunneling through them if they were any smaller. In fact, tunneling is a source of the current leakage that causes significant power drain and heating effects that plague today's high-speed and mobile technology. On the other hand, tunneling can also be beneficial in some areas, like computer flash memory, where tunneling is a fundamental technique used to program its floating gates, resulting in one of the most significant inventions that shaped consumer electronics in the last 2 decades. Just to show a little bit better how tunneling works, let's add a bit of visuals. Here's a short animation of an electron wave packet sent towards a barrier. Now pay attention to the dim spot on the other side of the barrier after the main wave packet is reflected. This dim spot represents the electrons that tunneled through the barrier, and it's dim because it was all based on a low probability to tunnel through. Here's another quick little example using a graph. Here, the line at x0 represents a tall but very narrow barrier. Because the barrier is narrow, a significant tunneling effect can be seen because the probability of tunneling through is higher. Lastly, let's take a quick look at this short video that shows how tunneling works in practice. Here we start with a thick barrier that makes tunneling so improbable that we essentially always get a bounce back. Now, as the thickness of the barrier decreases, we see more tunneling happening until the barrier is so thin that tunneling happens extremely frequently. Now, let's talk a bit about where we find quantum tunneling in nature. The first one worth mentioning is probably the nuclear fusion of stars, where the temperature in the core is generally insufficient to allow atomic nuclei to fuse together, if that was the only factor in play. There's something called the Coulomb Barrier that describes the electrostatic interaction between two atomic nuclei that get near each other, which they have to overcome in order to fuse together. Quantum tunneling is what increases the likelihood of overcoming this barrier, since most stars can't do that on their own. This tunneling is what allows atoms to fuse in the core of stars frequently enough to be sustainable. Though this tunneling is still something that happens with low probability, the sheer amount of nuclei in the core of stars is enough to sustain nuclear reactions for even trillions of years in some cases. Another place we also find quantum tunneling in nature is in the radioactive decay of atoms. Radioactive decay is the process in which atoms emit particles from their nucleus in order to become more stable, and the emission of the particle out of the atomic nuclei happens due to that particle tunneling outside of the nucleus. Quantum tunneling is also able to cause spontaneous DNA mutations, which can sometimes result in cancer and could also be a factor in how we age. Now, as far as technology goes, we already covered some of the challenges and some of the benefits that quantum tunneling presents. One that we haven't yet talked about though is the scanning tunneling microscope. This microscope operates by bringing an electrically charged and very thin tip close to some atoms in a material, like metal for example. When the tip is close enough to the surface, there's tunneling that happens between the electrons of individual atoms and the tip of the microscope. This allows us to measure exactly where the atoms are located so we can reconstruct it on a chart or an image. This is so precise that we can even use this to move individual atoms to other locations. Here is an image reconstruction of clean gold. Here's a silicon crystal. Here's a single-walled carbon nanotube, and here's graphite. Just for fun, here's what the scanning tunneling microscope in the labs of the London Center for Nanotechnology looks like. So all in all, quantum tunneling is not that complicated to grasp, but it does have a very significant impact on the universe. In fact, the universe would be a very different and dark place without quantum tunneling. Our technology is also something that will need to continue harvesting this phenomenon and overcoming the challenges it poses. As we get more skilled at working with extremely small scales, quantum tunneling is definitely something we'll hear more and more about in the future. I hope you enjoyed this video, and I also want to thank my patrons on Patreon for supporting the channel. I really appreciate the support. If you have any suggestions about science topics or recent science news that you'd like me to cover, don't hesitate to write it down in the comments. For more interesting science content, don't forget to subscribe to the channel and click the bell notification to be notified of all my uploads. You can also check out my website at respectyourintellect.com for all the information and videos on this channel. Until next time, thanks for watching, and remember, respect your intellect.